Swayam Prabha. Digital India. Educated India.
Welcome to the 12th lecture of the series. So, till last lecture we were discussing about the how to measure the correct emission and excitation spectra, and in that regard what we have learned is that if this is my fluorimeter, so here is my lamp and that lamp output is selected, the desired excitation wavelength is selected out of this excitation monochromator, and that light before directly exciting your sample over here is taken a small amount and detected in another detector, where this detector is named as R1, and then the sample fluorescence. So, here is your fluorescence, and I have emission monochromator is also over here, because you need to disperse the fluorescence to measure the intensity of each and every wavelength out of it, So, here is your emission monochromator, and then the selected wavelength out of this emission monochromator is directed to the detector. So, this is the S1 detector, and we have discussed about the total response of this emission monochromator and the detector together is, let us say, S lambda, that is the sensitivity, and so for that you will going to have the correction file for that, and so this S1, that signal is S1C, that means the corrected, Similarly, you will going to have this correction file for this R1 detector, isn't it? So, in this case, after the correction file, for this you will get R1C. Okay. Having said it, let us see that while you want to measure this emission spectra, which signal you should get, because here that lambda excitation is being selected here, lambda excitation, and here is your lambda emission, here is your lambda emission, The emission spectra means the plot of intensity is a function of wavelength for a given value of lambda excitation, So, for a given value of lambda excitation, let us say this is my given value of lambda excitation, lambda Ex. If I plot intensity versus lambda emission, then whatever you will get is your emission spectra. So, this intensity, obviously I need that S1 to be corrected, here this intensity is being detected where at this S1, this intensity is being detected at this S1. So, best I will write this S1. Now, this S1, depending on the wavelength, the response of this emission monochromator detector will change. So, that has to be corrected. So, it should be S1C. Okay. And Now, the fluorescence intensity depends on the excitation light intensity as well as the concentration. If concentration remains same, then it depends only on the excitation light intensity. So, I have to normalize with excitation light intensity, because in this case the excitation light is fixed, is only if this lambda excitation a particular wavelength. So, whatever the signal I will get in the R1 detector, that is I do not need to correct it, because it is absolute value, right. I do not have to correct it, I do not have to compare with anything, it is only one wavelength. So, simply this is S1C by R1, right. So, remember that if you just plot S1 versus lambda emission, you will not going to get the correct emission spectra, but in this case you will get the correct emission spectra. Similarly, for this so this is my emission spectra, right. Emission spectra. What about the excitation spectra? Excitation spectra is for a given value of lambda emission, right. So, you keep your observed lambda emission at a particular wavelength, let us say over here, let us say you fix your lambda emission over here, lambda emission max, right. So, for a given value of lambda emission, it could be anything here, 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 but I have chosen the maxima 1. So, for a given value of lambda emission, right, if I now scan the excitation wavelength, then if I plot the intensity of that particular lambda emission as a function of excitation wavelength, then as I showed in the last day, that it should resemble with the absorption spectra of the sample, provided the absorbance is low, right, absorbance is low and I0 is remain same for all these lambda excitation wavelengths, right. So, to fix that I0 same for this all the lambda excitation wavelengths, what I have to do? I have to divide it by R1, because that will going to give me the spectra of the lamp output, right. So, in this case, for a given value of lambda emission, let us say lambda emission max, if I plot the intensity versus lambda excitation, then what I am going to get is my absorption spectra, right. So, let me draw this absorption spectra is something like this way, right. So, this is my absorption excitation spectra. So, and which should resemble with the absorption spectra under those conditions which I mentioned, right. So, this is my so which signal I should plot over here, which I should plot over here. This is for a particular lambda emission, right. So, it should be S1, right, and I do not need to correct it, because I do not have to compare with the other wavelengths, right. So, only S1. So, S1, but I must divide it by the R1C, S1 by R1C, and that needs to be corrected, right. Okay. So, that is it for this measurement of the corrected emission and excitation spectrum. And now, let us move to another important measurement, which is the measurement of fluorescence quantum yield, right, measurement of fluorescence quantum yield. So, I have mentioned that fluorescence quantum yield is another important parameter of the fluorescence, where like intensity one parameter, emission maxima another parameter, quantum yield is the parameter, and another parameter is lifetime, which I have not discussed yet, but I will going to discuss later. So, what is the difference between fluorescence quantum yield and intensity, right? Fluorescence quantum yield is only the property of the molecule. It does not depend on the concentration of your species, concentration of your sample, and the excitation light intensity, right. So, this is a unique property of a molecule, right. So, this fluorescence quantum yield is defined as Kr by Kr plus Knr. That means, the process, right, the deactivation process which emits photon divided by total rate of absorption, right. So, this is the total rate of deactivation, that means the total rate of absorption, and this is the this Kr is the radiative process, that means it is going to give you the photon out of it, right. So, how are you going to measure it, right. So, let us say that you have a sample and its fluorescence quantum yield is phi f s, right, phi f s. So, I want to measure it. So, I can simply write the fluorescence intensity coming out of this sample. So, I will just write it as I intensity of fluorescence of your sample divided by the intensity absorption intensity of the sample, right. So, I A S. Now, this fluorescence intensity of a sample is a measurable quantity, right. You can just put your sample in the fluorimeter and you can simply measure what is the intensity is coming out of the sample. But this absorption intensity of the sample, right, this absorption intensity of the sample is not a directly measurable quantity, right. So, let me write over here I F S is fluorescence intensity of sample fluorescence intensity of sample, and IAS is the absorption intensity of the sample. Right. So, just to tell you, this is directly measurable quantity, this guy, but it is not. Okay. So, then there is a problem, right. Instead of that, if I have another molecule which I called as reference, and for that particular molecule, if the fluorescence quantum yield is known beforehand, right. So, let me take another molecule which is phi reference, and this phi f r, right, this is the fluorescence quantum yield of a known molecule which is referred as the reference molecule, right. So, here I will write fluorescence quantum yield of a known or known fluorescence quantum yield of a molecule, right. Of a molecule referred as reference molecule. So, in this case, this is nothing but I f r by I a r. So, I can simply write that phi f s by phi f r equal to I f s into I a r divided by I f r to I a s, right. Okay. Now, I know a equal to log I 0 by I. So, that will going to give me minus a equal to 1 over 2.303 ln I by I 0. So, this I can write as equal to 1 over 2.303 ln, this I is equal to I 0 minus I a, right, I 0 minus I a by I 0, this is 0, right. So, this is equal to 1 over 2.303 ln 1 minus I A over I 0. So, 1 minus I A over I 0 equal to e to the power minus 2.303 A is my observance, right. So, this is equal to 1 minus 2.303 A under the condition when absorbance is low. So, let me write here when A is small, right. So, what I will get over here after rearranging this thing, what I will get. So, this will cancel out. So, I A equal to I A equal to 2.303 A I 0, right. So, I can write this I A is proportional to A, right. So, I A is proportional to A. Just look at this equation, right. So, if this I 0 is fixed, right, if the I 0 is fixed means that when you will going to measure the intensity of the fluorescence for your sample and when you will measure the intensity of fluorescence of your reference, in both the cases the I 0 has to be fixed, the intensity of the excitation light has to be fixed, right. In that case this I A can be replaced by this A. So, what I can write? I can write I A of my sample is equal to 2.303 A of my sample into I 0, this is my excitation light intensity, right, for a particular lambda excitation. So, do not forget that. So, this is for the particular lambda excitation, right. So, for this lambda excitation. Similarly, I can write I A of R, that is the reference, is 2.303 absorbance of this reference, is not it, I 0 that lambda excitation. So, now I will replace these two in this equation. So, these two I am going to replace in this equation. Here IAR, IAS, right, I am going to replace it. So, if I do so, then what I am going to get is phi f of your sample is equal to phi f of reference, intensity of fluorescence of the sample divided by the intensity of fluorescence of the reference into absorbance of the reference where at that lambda excitation, right, silent over here, divided by absorbance of the sample. So, you see in this equation this quantity is known quantity, known, measurable from the fluorimeter, and this is measurable from the spectrophotometer. So, what you will going to get is the fluorescence quantum yield of your sample. So, what reference molecule people generally used, I mean which are well known. So, for example, one can use quinine sulphate in 0.1 molar sulfuric acid. So, for this quinine sulfate in 0.1 molar sulfuric acid. This phi f is known, right? This is 0.577. So, you can use. So, you can also use rhodamine 6G in ethanol. This is known 0.940, 0.940. So, there are several such kind of known molecules are there in the literature, which you can use depending on your requirement. What is the requirement? Requirement is your sample and this reference molecule should absorb at your lambda excitation. If you have taken a reference molecule which does not absorb where your sample absorbs, then you will not be able to use that molecule for your reference molecule. Another important point here to tell you that if the quantum yield of your sample is not very much comparable with the reference, then there will be lot of error in your measurement, right. So, suppose the sample quantum yield of your sample is like a 0.01 and you are taking a rhodamine 6G as a standard over here, that is reference sample 0.94. So, there will be too much of mismatch, right, because this rely on the intensity ratio. Here you see that this is the intensity ratio of the fluorescence, right. So, this intensity ratio has to be measured very correctly, otherwise the error on the measurement will be very high. So, one has to use a similar quantum yield standard. If your sample estimated quantum yield is 0.01, then you should use your reference as 0.1 or 0.05 or like that. You should not use 0.9. If the quantum yield of your sample is about 0.5, 0.6, then you use a reference whose quantum yield is about that, right, 0.5, 0.6. So, that is just another thing to mention. Another thing is that you may ask that what if that I am the first person to measure the fluorescence quantum yield, that means no reference is known, right, that is also possible, and we usually use the integrating sphere for this measurement, which I decided not to discuss in this case because of the time constraint, but it is possible. You can check in the literature later on. Okay, so, but this method, this comparative method of the measurement of fluorescence quantum yield is well accepted all over the world, and people are every day using this method. So, so this is good enough for this basic course, right. Okay, so now let us move to another topic. So, here what I have written here is solvent effect of fluorescence, right. Earlier what we have seen is the solvent effect on absorption spectra, and we have discussed about two different cases where the ground state dipole moment is more than the excited state dipole moment. We see that on increasing the solvent polarity, right, there is a blue shift in the absorption maxima of the particular molecule. Whereas, when for other molecule where the excited state dipole moment is more than the ground state dipole moment, right, we would have we have estimated that there will be a red shift in the absorption maxima as you are going to increase the polarity of the solvent. Right. And based on that, we have also discussed this ETN scale of the polarity, and now it is time to look at that what is the effect of this polarity on the emission spectra, right. We talked about the absorption spectra, now we have to talk about the emission spectra. Okay, so for this emission spectra, right, I will just simply start with this molecule which has the dipole, right. So, that means the ground state dipole moment is mu g, and if you excite it, the excited state dipole moment could be will be mu e, right. So, I will just simply draw that molecule as like here, over here. This is my molecule, and this molecule has a permanent dipole over here. It could be mu g or mu E depending on whether the molecule is present in the ground state or in the excited state, right. Okay. And so, whenever you will put this molecule in a solvent, right, what will happen? This solvent molecule will going to solvate this species. So, as I showed in earlier, that these are the solvent molecule, will try to stabilize this solute dipole, right, and negative charge will be over here, right, for the stabilization. And what we will going to see is so this is my solute. Let me write clearly, this is my solute, these are my solvents. Right. So, now because of the arrangement of the solvents around the solute, right, a reaction field will be generated, right, a reaction field will be generated like this way. So, I name this reaction field as R, right. So, this R is nothing but the electric field in the solvent induced by the dipole, induced by the solute dipole. So, this is electric field in the solvent induced by the solute dipole. And so, that means this reaction field, right, this R will depend on the magnitude of the solute dipole moment, right, mu, right, and also the radius of the solute and how easily that solute can induce, can polarize the solvent molecule. So, I am going to have 3 factor which will define this reaction field R, and we will continue this on the next lecture. Thank you.